today, and we are talking compaction targets after you add the chemical. So whether that be quicklime, LKD, or even cement, the OMC and maximum dry density are going to change for that soil. So from standard proctor to compaction curves after adding those chemicals, we want to make sure we test the soil correctly here in the lab to be sure you've got the right numbers out there in the field.
Chemical treatment increases the optimum moisture content and decreases the maximum dry density. These shifts are normal and we should expect them. They relate to changes in the soil structure as the chemical reacts. Recognizing these new targets ensures we compact the soil the way the treated material wants to behave in the field. Using these updated targets helps to avoid undercompaction, often caused by compacting treated soils too dry, or chasing densities the material can no longer achieve. If we keep using the original targets, we risk fighting the material instead of working with it. Results are only as good as a sample, and soil conditions vary throughout construction sites. Sample multiple locations and consider if each should be tested individually or if a composite sample is appropriate. When looking to see the possible degree of improvement after chemical treatment, gathering material that reflects both typical and extreme conditions supports a more complete picture of performance. Is it sandy? Is it a fat clay? What's the bulk of the site look like? Before we can run a compaction test, we want the soil to reflect what's actually happening in the field. Air drying lets the moisture come down naturally and keeps the material structure intact. Spreading the soil thin and using fans helps everything dry evenly. Once the soil is ready, we screen it over a 4 mesh to remove oversized particles and break clods apart without crushing the natural particles. Many times we like to start by looking at the untreated soil as a baseline with a standard proctor. We prepare several batches of the soil at different moisture contents, starting on the dry side and moving towards the wet side until we've bracketed the peak. Ideally, this is 2 points on the dry side, 2 points wet of optimum, and 1 right near OMC. Each batch is compacted in 3 lifts, so the final layer finishes just above the mold and into the collar. Using an automatic compactor can really help here because it keeps each blow consistent from point to point. After compaction, we take a sample from each point and oven dry it overnight to determine the moisture content. Once those numbers come back, we can plot them to build a compaction curve. When adding chemicals to the soil, it's important to make sure that everything is blended thoroughly. A mechanical mixer is a must. Hands and spatulas just don't do it, especially for fat clays. Once the chemical is added to the soil starts to behave differently, and that's exactly what we expect. The compaction curve will shift, and that isn't a surprise. It's a sign the treatment is changing the soil structure the way it's meant to. Working with lime-treated soils adds a few important steps. First, we bring the moisture content slightly above the expected optimum, usually 2 to 3% higher. That extra water gives quicklime or kiln dust the moisture it needs to completely hydrate. After a good mix, we let the soil mellow. In the lab, that usually means sealing it in a plastic bag or bucket overnight so the calcium oxide component can completely hydrate. In the field, mellowing can look a little different. Kiln dust doesn't need a mellow period, while a typical mellow period for quicklime is about 4 hours. Back in the lab, after mellowing, we remix the material and allow it to air dry back down below the optimum moisture content. From there, we run the compaction test the same way we did before. A few points across a range of moisture contents so we can see where the new treated curve lands. While working with lime can be more forgiving on timing with mellowing overnight, you've got to work quick with cement. Once the water and cement meet, hydration starts and timing becomes a big part of the test. After everything is blended, we don't want to wait around. We move straight to compaction. That keeps the moisture density relationship accurate and prevents the early formation of bonds from shifting the results. From there, the process looks familiar. 3 lifts, consistent energy, and carefully tracking moisture so we can build a clear curve for the cement-treated material. Once the compaction work is finished and we've got our oven-dried moistures, we can start to see the full picture of how the soil behaves. Each compaction point gives us a weight at a known volume and the moisture content from the oven-dried sample. With those values, we calculate the dry unit weight for every point. When we plot these dry unit weights against water content on a graph, the familiar compaction curve begins to form. Compared to an untreated curve, the differences are normal and expected. They reflect a change in the soil structure after the addition of the chemical, not a loss in strength. When field teams evaluate moisture and density, the goal is to compare the results to the curve for the treated condition, because that curve represents how the material is designed to perform. So what are the takeaways? Chemically treated soils behave differently than untreated soils. A lower maximum dry density does not mean lower quality. It reflects how the soil structure changes during treatment. And most importantly, Compaction should be based on the curve that represents the treated condition. That way, moisture and density targets in the field match the soil we're actually working with.